In the second talk, I would like to introduce how we parallelize our static bug detector via a pipelining technique. The title of this paper is Pipelining Bottom-up Data Flow Analysis. This talk also consists of 4 parts: the background, the approach, the evaluation, and a brief summary. In practice, to run in parallel, conventional approaches are often implemented in a bottom-up manner. In a bottom-up analysis, callees are analyzed before callers, and the analysis results of a callee function are recorded as function summaries, which summarize the function behavior. For example, we have 3 functions where the function f calls the functions g and h. So we firstly analyze the function g and h, generating function summaries by recording whether they will return any invalid pointers. With these summaries, we then analyze the caller function f to check whether the invalid pointer may be improperly used. Bottom-up analysis is easy to parallelize. This is because functions without calling dependence can be analyzed in parallel. So in the example, we can analyze the function g and h at the same time and then analyze the function f. However, as pointed out by recent studies, the parallelism is limited. As shown by the graph, the x-axis is the rolling time and the y-axis is the CPU utilization rate. We can observe that the CPU utilization rate drops off at the second half of the analysis. This is mainly because the call graph is usually a tree-like graph. The bottom half of the call graph is usually very sparse and so has sufficient parallelism. The top half of the call graph is very dense, so the parallelism is limited by the calling dependence. So a natural question here is that, is there any chance to improve the parallelism so that the analysis can finish earlier, just as shown by the red curve? Intuitively, it is not necessary to start the analysis of a function until we get all the analysis results of its callees. So our basic idea is to relax the calling dependence between functions. Ideally, we can partition the analysis task into multiple parts so that they can be pipelined as shown by the graph. So the remaining problem to solve is how to partition the analysis of a function. Before introducing the partition method, let us look at what kind of function summaries we need to generate for a value flow analysis. Here we use the null point analysis as an example. Given a function, null point may come from 3 places: from a caller function via the function parameter, from the current function, or from the callees via the function return value. According to where a null pointer may come from, we generate 3 types of function summaries. The type 1 summary is a value flow from the function parameters. Type 2 summary is a value flow from the null pointer in the current function. The type 3 summary is a value from a null pointer returned by callee functions. Here is an example where function foo calls the function bar. The red part is the data dependence graph of the function bar, and the black part is the data dependence graph of the function foo. Following a conventional bottom-up analysis, we first analyze the callee function and generate 2 summaries. The type 1 summary, which is a value flow from the function parameter a to the return statement, and the type 2 summary, which is a value flow from a null pointer to the return statement. Second, we analyze the function foo using the function summaries. We generate a type 2 summary and a type 3 summary. One is the value flow from the null pointer in the current function to return p, and the other is from the null pointer in the callee function to return p. So in our approach, we partition the analysis task of a function into 3 parts. Each part generates a type of function summaries. Given a pair of functions where foo calls the function bar, a conventional approach conservatively assumes that all the analysis tasks in the caller function depend on the all analysis tasks of the callee function. So in the conventional approach, we need to finish all tasks in the callees and then start to analyze the callers. However, we observe that not all such dependencies are necessary, as the red dependence relations actually can be removed. So we have the opportunities to improve the parallelism. Let us look at the example. We can observe that the type 2 summary of function foo depends on the summary of function bar. That is the blue path in the figure goes through the yellow path from the function bar, so the black dependence is necessary. The blue path doesn't go through the type 2 summary, so the yellow path of the function bar, so the red dependence is not necessary and can be removed. After removing the red dependence, we can schedule them in a pipeline manner. After generating the type 1 summary of function bar, we can generate the type 1 and type 2 summary of function foo. Finally, we can generate the type 3 summary of function foo after generating all summaries of the function bar. So for this example, our approach doesn't need to wait the analysis of bar to start the analysis of function foo, so our analysis is more fast, more efficient. In the paper, we formalized the pipeline idea in the IFDA's IDE framework for a wide range of problems, such as the NSS problem, the problem securing information flow, and so on. These problems have a common feature that they can be reduced to a graph reachability problem, just like our value flow analysis. As for evaluation, we use similar benchmark programs as before and compare the pipeline method to conventional parallel design in terms of CPU utilization rate and the speed up. These figures show the CPU utilization rate for N9 in some of our benchmark programs. The red curves are the CPU utilization rate of our pipeline approach. The blue ones are that of the conventional approach. It is clear that our approach has higher CPU utilization rate than the conventional one, and so can finish the analysis earlier. This figure shows the speed up against the number of threads. Different lines represent the speed up of different benchmark programs. With more threads, the benefits of our approach is more apparent, leading to 2 times to 3 times speed up. Such a speed up is not trivial in practice. It is enough to make an originally impractical analysis practical. For the pipeline approach, there are 2 factors that may affect its performance. First, we have shown that with more threads, our approach is more effective. If we only have 1 thread available, neither of our approach and the conventional one can perform parallel analysis, so they will have similar performance. Second, the effectiveness of our approach is also affected by the sparsity of the call graph. Recall that our pipeline approach relaxes calling dependence to improve the parallelism. So if a call graph is very sparse and has little calling dependence, then the benefits of our approach were not that apparent. As a brief summary, our approach relaxes the calling dependence to improve the parallelism of bottom-up data flow analysis. So to take advantage of multi-calls, let us pipeline not simply parallelize data flow analysis. Thanks very much. That's all.